Hello everyone, myself Anirban Vishwas. Today I am going to explain the chapter 2 for the subject digital circuit design using Verilog. In this chapter, it basically describes the different design in which we can write the coding part. So let's start this. First, what is a module? It's basically the basic unit of description in Verilog. A module describes the functionality or structure of a design and also describes the ports through which it communicates externally with other modules. The structure of a design is described using switch level primitives, gate level primitives, and user defined primitives. As you can see, here is the basic syntax of a module. We will write here is the module, and then we will write the module name, then we'll write the port list, and then we will declare whatever we will give register where parameter input output it out, then we'll write the function, and then finally we'll write the main code part, the statements, and at the final we'll giving the end module. Declarations are basically used to define registers and parameter that is used within the module. Statements are used to define the functionality or structure of a design. Let us take an example here of a full header. Here we'll start using a kind of module, and then we'll define the module name, that is half header, and we'll giving the port name, that is input and output, everything a b sum and carry. Then we'll define the input part, that is a b, and the output part sum and carry, as you can see. And then we will assign stack to sum is equal to the sum part, and assign stack 5 carry, that is a carry part, and then we'll get the end module. And here is the basic example of how we'll proceed with the coding part. Next, all ports are of size 1 bit since no range has been specified. These four ports are of the data net data type since no declaration has been specified. The module contains two continuous assignment statements that describes the data flow behavior of the half header. The statements are concurrent in the sense that their order of appearance within the module is not important. Execution of each statement occurs based on event occurring on net A and B. So here we come finally within a module, a design can be described in the following style. We have four different styles in which we can write the coding part. First one is data flow style, second was a behavioral style, third one is structure, and at the last the mix of all the above three. So we'll come across one by one. The next is what is delay. Uh, all delays in the Verilog HDL modified are specified in terms of time units. As you can see, here is the example assign hashtag 2. This hashtag 2 defines that after 2 nanoseconds of delay, this part will be executed. As you can see, here is the part how it is written, time scale 1 nanosecond per 100 per second. What's this? This signifies that one time unit is to be treated as 1 nanosecond, and the time precision is to be 100 per second. So in here, as you can see, hashtag assigned to, here it will be 2 nanosecond per 100 uh, per 100 picosecond. The hashtag 2 refers to 2 nanosecond. If no such compiler directive is specified, for example, if we don't define any time scale, the Verilog HDL simulator may default to a certain time unit. This default time unit is unspecified by the IEEE Verilog HDL standard. Now we come across the first uh, style of describing. First one is data flow style. The basic mechanism used to model a design is the data flow style. In the data flow style is the continuous assignment. In a continuous assignment, a value is assigned to a net. As you can see, assign delay LHS net is equal to RHS expression. Anytime the value of an operand used in the right hand side expression changes, the right hand side expression is evaluated and the value is assigned to the left hand side net after the specified delay. If no delay is specified, the default is 0 delay. Let's come across an example. Here is a 2 to 4 decoder circuit. Here is the example of how we will start with it. We have given time scale is 1 nanosecond. We have written module since it's a decoder 2 is to 4 circuit, and we have decoded all the port list A, B, enable and Z. So input are the A, B and Z enable, and output are the uh, 4Z, Z0, Z1, Z2, Z3. 0 is to 3, Z Z0, Z1, Z2, Z3. And where are the A bar, B bar? Then we will assign all the, will give the assign, that is the basic way of describing the data flow style. Assign hashtag 1 A bar is equal to negation of A. Assign hashtag 1 B bar is equal to negation of B. Assign hashtag 2 Z0 is equal to negation of A bar, B bar, and like this we'll assign all the Z0, Z1, Z2 and Z3, and finally we'll end module. The first statement at the time that begins with a backcode. This is an example of a compiler directive. A net declaration declares the two words A bar and B bar. The module contains 6 continuous assignment statements. Next, we will see the timing diagram here. So, when enable changes at 5 nanosecond, statement 3 here, the statement 3, that is Z0, statement 3, 4, 5 and 6 are executed. This is because enable is an operand on the right hand side of each of this continuous statement. Z0 get assigned, so Z0 get assigned to its new value, which is 0 at time 7 seconds. Yes, it will be after 2 nanoseconds. So after 5, then again 2 nanosecond to 5, 6, 7, after the 7 second. When A changes at 15 nanosecond, statement 1, 5 and 6 executes. You can say statement 1, 5 and 6 execute. Since a bar is changing, so 1, 5 and 6 will execute. Execution of statement 5 and 6 does not affect the value. So that execution of 5 and 6 do not affect the value of Z0 and Z1, Z0 and Z1. Yes. And execution of statement 5, that is Z2, causes Z2 to change at 0 to 0 17 nanosecond. Here we'll see Z2 to 0 at 17 nanosecond. Execution of statement 1, that is ever negation, causes ever to get its new value. We'll see here ever at new value at 16 nanosecond. Since ever changes, this in turn causes 70 to change value to 1 at 18 nanosecond. Notice that the continuous assignment model data flow behavior of the circuit, the structure is implicit, not explicit. In addition, continuous assignment execute concurrently and they are order independent. So here is a basic example of a data flow style. Next, we'll come across the behavioral style. The behavioral of a design is described using procedural construct. These are in we can start with an initial statement, or we can do it that with an alloy statement. In initial statement, the statement executes only once, and in alloy statement, this statement always executes in a loop. That is, the statement is executed repeatedly. Only a registered data type can be assigned a value in either of these statements, such a data type retains its value until a new value is assigned. All initial statements and alloy statements begin execution at time 0 concurrently. Here we'll see an example of behavioral style. Here is a 1-bit full adder. So module full adder sequence. We'll describe all the port list A, B, C in, sum, C out. We'll describe the input parts A, B and C in. You can see in here A, B, C in, and output sum and count. Next the register sum and count, and register T1, T2 and T3. We'll this this is an example with the always statement. So we'll start with the always at the rate A or B or C in, then begin. This is basically a begin. Then the sum part is described. Sum is equal to a plus b and c in. You can see sum. Then T1 is A and C in, T2 is B and C in, T3 is A and B, and C out is T21 or T2 or T3 and N module. So, the module FA sequences three inputs and two outputs, as I have already and are declared to be a type register because these are assigned values within the alloy statement. The alloy statement has a sequential block, as we have described, begin and end pair associated with an event control uh, expression following with the asterisk character. This means that whenever an event occurs on A, B, or C in, the sequential block is executed. After the sequential block completes execution, the alloy statement again waits for an event to occur on A, B, or C in. The statements that appear within the sequential block are examples of blocking procedure assignments. Delays can also be specified in two different forms: inter-statement delay and intra-statement delay. In inter-statement delay, a statement's execution is delayed, and in intra-statements delay, between computing the value on the right hand side expression and its assessment to the left hand side. This is the delay between computing the value of right hand side expression and its assignment to the left hand side. It's an example of inter-statement delay. Sum is equal to A or B or C in hashtag 4 T1 A and C in. And here is an example of inter-statement sum hashtag 3 A or B or C in. If no delays are specified in a procedural sense, zero delay is the default. That is, assignment occurs instantaneously. Here is an example of an initial statement. Time scale, we have given 1 nanosecond per 1 nanosecond. Module test, pop and feed. Output will be the pop feed. Register the pop feed. Begin the initial begin. Pop we have given 0. Feed we have given 0. This is the statement 1. This is the statement 2. Then we have given 5-second delay to pop 1, and it will have the value will be 1, as you can see in here. And the feed after 8 nanosecond, the value will be 1. Again the pop after 6 nanoseconds of time, that is 14 nanosecond, that will be total. It will have a 0 value. And feed after 16 nanoseconds of time, it will have a 0, again 0 value. And N module. Next we come across describing in structural style. Structures can be described in Verilog HDL using built-in gate primitives at the gate level, switch level primitives at the transistor level, user defined primitives at the gate level, and module instances. Let us see an example of a structural design. It is of a full adder figure. Let us see the figure. This is the figure. So we'll start it using module full adder. The port list A, B, C, sum, and C out. As you can see in here, A, B, C, and sum and C out. Input will be the input are given A, B, C in, output sum and C out, where S1, T1, T2, T3. Let's see in the diagram. Input A, B, C in, output sum output in the where S1, T3, T1, T2. Then then all the XOR modules are described. Let's see the X1 and the X2. So see how it is. The XOR X1, the S1 is connected to AB, and X2 in X2 the output is sum, which is connected to S1 and C. Let's see in the diagram. This is the XOR X1, where the S1 is the output and AB is the input, and this is the another X2 XOR, where sum is the output and S1 and T3 are the input. Then the N module are described: A1, A2, A3, where in A1 T3 is the output with output, and AB are the input. Similarly, A2 and A3 are, let's see in the diagram, A1, A3 and A2. These three are the AND statement, and this is last model, that is the OR, where C out is the output and T3, T1, T2 are the input. See, OR, C out is the output, T1, T2, T4. Lastly, AND module. In here, the gate instantaneous can appear in any order since no sequential is implied. Pure structures definition of XOR and an OR are built-in gate primitives. X1, X2, X3 are etc. are the list of signals flowing each gate are its interconnection. The first one is the output of the gate and the rest are its input. You can see first is the output and rest are its input. A 4 pulsator can be described by instantaneous. Next, a 4-bit full adder can be described by instantaneating 4 1-bit full adder module, which means that we can describe a complete module within a module. Let's see the example in here. We have is a 4-bit full adder. Let's see module. Here is the module name, 4-bit full adder, and these are the port list: FA, FB, FCin, FCR, sum, and FCR. The parameter is the size equal to 4 since it's a 4-bit full adder. Input size 1 FAFB 4 is to 1. That will be FA4, FP4, FA3, like this, FA1 to FP1. Same output as the 4 is to 1, the F sum. Input is the FC in, you can see in, and final output is the FC out. And where is the 1 is to 3 ftemp. Ftemp 1 is the ftemp 1, this is the ftemp 2, and this is the ftemp 3. Then in this module, the 4 adders thing, that this complete module has been inserted. Now we'll see it how it's written. FA1, in the FA1, uh, A and FA1 are connected, B FB1 connected, C FC connected, sum F1 connected, and C out with FM1 are connected. Similarly, FA2 is written in the same order. FA3 is written in a slightly different order, where the AN the in A, B, C in these parts are not written. It will be taken directly from here. See, the FA3 will be with the A part, since this module is been directly inserted in here. FB3 will be with B, F temp2 will be with sin, F sum 3 will be with sum, and Ftemp3 will be with C out. Similarly, FA4 is also written in the same order. And lastly, we will give the end module, and the module will be stopped. Now let's see the last, that is mixed design style. Within the module, structure and behavior constructs can be mixed freely. That is, a module can contain a mixture of gate, instantaneous, module, instantaneous, continuous assignment, and always an initial statement, amongst others. Remember, only a register data type can be assigned a value within the statement. Here is an of 1-bit full adder in a mixed design style. Module, we have given the module name FA full adder. Mix A, B, C in, C sum, C out. Input A, B, C in, output sum, C out, register, that is C out, and register T1, T2, T3, and wire S1. We have described the XOR gate X1, S1, A, B, and this uh, this, if you can remember, is the behavioral structural design, and this is the structural design that we have just completed. It's a always statement, so always at the A or B or C in begin, T1 is equal to A and C in, T2 is equal to B and C in, T3 is equal to A and B, C out is equal to T1, T2, T3. As we have known that always will have begin and end statement. So if we begin, we have to end it, and then assign. As you can remember, this is the data flow where we assign anything. The assign sum is equal to S1 of C in. and finally we will give the end module, with which the module will end. Executing execution of the get instantaneous occurs whenever an event occurs on A or B. The alloy statement executes whenever there is an event on A or B or C, and the continuous statement, which is this one, executes when there is an event on S1 or C. Thank you.